This video will move into Chapter 6. Specifically, we're going to focus on Section 6.2, the Law of Sines. 6.1 does a little more applications of right triangles. We've seen a little bit of that back in Chapter 4. They just do a lot more. How many situations we can actually assume there's a right triangle when trees grow and buildings are standing in signposts and other such problems. There really are a lot of right triangle situations. And for any of you who go into physics, engineering, you'll see how often that's one of the first steps. That in so many of your problems, that if something happens at an angle, that you want to break it into its XY components, and we will always just use right triangles for that. But now, when we move into section 6.2, before I introduce the law of sines, let's establish a few situational facts here. First thing, now when we look at triangles, we're not assuming any right triangles. In fact, while law of sines does work with right triangles, it ends up just being an exercise using the basics of trig functions, but it can apply for right triangles, but it's really made for any type of a triangle. So that's definitely not a right triangle, and I intentionally tried to make sure I didn't draw it as a regular triangle where, you know, all angles, all sides are the same. This could even be an obtuse triangle where one angle is actually bigger than 90 degrees. So this is what we're going to start off with. And again, we need to get a couple of little established facts before I introduce law of sines. So when we look at generic triangles, we often refer to them by the letters that go with their vertices. So this first triangle, this can be referred to as triangle ABC. And just because you look at each corner, I have each of these vertices labeled as angle A, angle B, and angle C. And that's the first thing I want to establish. That back in geometry, some of us got used to identifying angles. Like if we wanted to look at this angle, we could call it angle BAC or angle CAB. But either way, we needed both pieces to make it clear we're referring to this corner. But you especially needed that in earlier geometry classes because there could be multiple triangles. That if I had a picture like this, A, B, C, D. Oh no, I've got triangle ABC, I've got triangle ABD, I've got triangle ACD. So there's so many built-in triangles here, but we're not going to look at any situations like that. So with this slightly easier situation, now when we look at angles, we can just refer to the vertex. So if I just write A equals, capital A equals, that is literally referring to what is the measure of angle A. And that also, we in geometry, referring to angle A, and we had to use this notation, and that some of us, we also had to distinguish, this just refers to angle A, this refers to the measure of angle A. But again, we're simplifying that notation here. This covers both. A refers to the angle or the numerical measure that goes with it. Either one is pointing us to this corner. Okay? I could do the same thing for angle B, angle C. But the next thing I want to establish are the sides. So if I have a triangle, I have the three angles, and we could use other letters, but you'll notice in this section, we pretty much always just stick with ABC. So we will have that kind of picture given sometimes. Other times they'll just give us information. Capital A equals this value. Capital B measures this value. But we also need to talk about the side lengths. So we have three sides to go with our three angles, and we always refer to the sides by which angle they are across from. So if this is angle A, then this is the side across from it. This would be side A. And we use lowercase letters for the sides, capital letters for the angles. So little a would be the length of the side directly across from angle A. So we're not going to get ideas of opposite, adjacent, and hypotenuse here. Those ideas only go with the right triangle. Here, everything is about what side, which angle is that side across from. So this side is across from this angle. This would be side B. This side would be across from this angle. This would be side C. I will say, for print letters, for some people, capital C, lowercase c, those can look close. So I'm just trying to do it by size. Hopefully you could see that's a bigger C than that one. Some people like to use cursive letters just to make that a little bit more clear. But that's your choice. I will stick with the lowercase print letters. But just for some people, they'd rather use the script just so it's a little bit more distinguishable, especially angle C versus side C. Over here, if we had a triangle that looks more like this, same thing, everybody. And, I don't have to start A from the bottom left corner. I could start A here, A, B, C, like that. This would be side A. That would be across from angle A. This especially seems weird. Some people just always try and go in a straight line. So go back to the first one. Straight line, straight line, straight line. And everything kind of worked out by just forcing that straight line out of the angle. And that kind of works here, but you got to make sure your line comes out of the middle of the angle. So out of the middle of the angle, you'll eventually get over to here. And that's side A to go with angle A. This one's easier, going directly across. That would be side B to go across with from angle B. But up here, sometimes that's a little weird. Some people try and do things like this, but you got to stay inside the angle. So inside the angle takes you over to here, and this would be side C across from angle C. So that's my first bit of notation that we have to have established. And now that we do have that established, now we can actually introduce the law of sines. If you read in the book, this is very similar to Pythagorean Theorem. Most people remember the law of sines as a formula, even though it's more of a statement of geometry and a relationship. So similar to Pythagorean Theorem. Most people remember Pythagorean Theorem as a squared plus b squared equals c squared. But that's kind of the little shortcut. That's kind of the, assuming we already know we have a right triangle. Formally, the Pythagorean theorem reads, if we have a right triangle, the squares of the length of the sides of the legs, the sum of those two squares is equal to the square of the length of the hypotenuse. But again, the a squared plus b squared equals c squared shortens that, and a lot of us make that work very easily and effectively. Similar with law of sines. Most people remember law of sines as this formula that I'm about to write. I have sine of angle A over side A is equal to sine of angle B over the length of side B is equal to sine of angle C all over side C. And that's what most people remember. But formally what this says is that the ratio in any triangle of the sine of the angle divided by the side, the corresponding opposite side, is always an equal ratio. So it doesn't matter if I use sine of angle A over side A, or sine of angle B over side B, or sine of angle C over side C. These will always be the same ratio. I mean, to be honest, we could even do an opposite formula. We could do it the other way. I could have little a over sine A is equal to little b over sine B is equal to little c over sine C. So that's what law of sines really gives us. And what we will see in just a moment when we start doing some problems, this will allow us to essentially find any side and angle that we're looking for. Our directions for all of these problems pretty much always say something like, complete the triangle. But just what does that statement even mean? If we're asked to complete the triangle, that literally is telling us to first thing, well, it's two things really. It's to find the measure of all angles and to find the length of all sides. That's what we are looking to do. So this is going to be a section where we need our calculators. I'll show you some of the arithmetic when we get to that part. And we'll also need to have some rounding directions. So for these purposes, let's stick with the same directions for all. Let's complete the triangle, and that would be my directions. I won't keep saying this, but that's the basic direction, but I have to give you rounding directions. Complete the triangle. Let's round all angles to the nearest degree. So that establishes we want degrees, not radians, and that's the more common thing here. If you look at some of the word problems that come up, and I'll mention that very briefly at the end of this section, that if you look at these problems, most of our common everyday examples, most people use degrees. So that kind of makes sense, and the nearest degree, the nearest whole degree, so if we have fractions or decimals, which we should expect, we'll round to the nearest whole number. And let's round all of our sides. Let's go here to the nearest tenth. Tenth of an inch, tenth of a mile, tenth of a foot. That really doesn't matter. You'll see the units here. We're not trying to play any games or trick you with units. If one side is measured in feet, well, then all the other sides will be measured in feet. If one side is measured in inches, well, then all the other sides will be measured in inches. This is just, again, get us to the nearest tenth. So let's start nice with the first problem. I give you this picture. So now our first problem. Complete the triangle, and this is your given information. You are given triangle ABC, and I give you angle A is 37 degrees, angle B is 59 degrees, and I tell you that side C is 8.7. So we want to, again, complete the triangle based off of this. And just in one extra second, I wanted to give you one where I gave you the triangle, but to realize most of these problems would start off, instead of giving you this picture, would just say things like given A equals 37 degrees, B equals 59 degrees, and little c equals 8.7. Having this information, you can draw a triangle and fill in your pieces, or you can just work directly from this information. Either way will be fine. Now, you'll also notice one other quick thing. I'm not even trying to draw this triangle to scale. And that's something that kind of throws people off. The ones in the book, sometimes they give you a triangle that's sort of drawn to scale, but this is not an exercise in just using a ruler or a compass or any kind of a protractor. It's trying to get you to realize how Law of Cosines does this, and it's really just trying to give you the picture as a little bit of a reference point. And the second thing, this is our first problem, we'll do several more, but this is the nicest situation, everyone. In this one, I always have to give you 3 pieces of information. You'll see that as we go along a little bit, but what pieces do I give you? Well, in this picture, in this situation, I gave you 2 angles and 1 side. And this happens to be the most friendly of these situations because nothing bad can happen here. So, what is so good about having 2 angles? And what do I mean by what's good here? You'll see in the next several examples, I'll give you 1 angle and 2 side lengths. So having 2 angles versus 1 angle and having 1 side length versus 2, that little situation will have a few little different possibilities that can happen. So again, this first one is nicest because anytime you know 2 angles, you can always immediately jump and get the third. I'm not using any law of sines or anything here. I'm just using triangle facts that A plus B plus C, that the sum of the angles in any triangle, not just a right triangle, but any triangle, that always has to add to 180. So now some people can just do a little good rational thinking. Others literally solve this equation. You know A is 37, you know B is 59, and now you could solve for angle C. So I do a little arithmetic here. My 37 plus 59, that gives me 96. And when I subtract that from the 180, I get C is 84 degrees. And little things, everybody, how you give your answers, I have no problems at all. If, just like I did here, you just have it labeled and underlined, you're going to find other pieces. So make sure it's clear that I could find all the pieces. Some people like to go back to the top and just keep a new list. Okay, well now I've got C is 84 degrees. That part is done. Other people fill it in the picture. I don't mind where you put it, everybody. I just need to be able to find your answer somewhere. So I'll put it here as well. So I've got the 37 here and the 84 here. And now, where do I go from here? This is where Law of Sines is coming up, everybody. And it's not obvious from the first part, but now that we're actually starting to use it, to realize, how is this formula helpful? Even though it's got 3 pieces, we'll always be just using 2 at a time. And the way we will use this is that we will need one angle and side that correspond together, and then we will be able to use the other angle or another side that we know to find the missing angle or side that corresponds with the given angle or side. Sounds complicated, but let's see what we have here. I've already just found angle C, so now I've got angle C and side C. I've got this corresponding pair. So I can plug that in here. And this doesn't matter how you set up your proportions, everybody. It's just about being consistent, but I'm a creature of habit, so I always like to start with my proportion with the sides that I know together. So I'll get sine of 84 over 8.7 equals. Now, what do I want? Well, I'm missing side B and side A. And this doesn't matter any order. I'm going to have to do almost the same thing twice. I'm going to start off finding side A, which means I need to know angle A. So I've got that. So I come to my other side. I've got sine of 37 over little a. And this is what I was saying a moment ago, everybody. We'll always get a proportion, and we can only solve for one piece of that proportion. So in this scenario, well, I could solve for A. I'll cross multiply. I'll get A times sine of 84 equals 8.7 times sine of 37. I'd strongly recommend saving your calculator for the end, everybody. So right now, I'm not going to do any arithmetic on my calculator yet. I'm going to finish solving for A. That's A times sine of 84. I'll divide the sine of 84 over. And this, I'll do all of this at once on my calculator. Again, make sure you're in the right mode. So just quickly checking your mode. I'm already in degree mode. So now I could just jump right in, do this work. 8.7 times sine 37. My calculator, like many of yours, opens a parenthesis when you would input a trig function. So I've got to close that, divided by the sine of 84. Good habits. You should close that parenthesis. You would get it correct if you did not. And now we're getting our answer, and now is where we should round. We said our side lengths will go to the nearest tenth, so I'll look at the hundredths place, 5.26. I'll round and say A is 5.3. So I keep saying, everybody, I could find angle C is here, side A is here. So I'll just do my work for side B right here, and that would be the work for complete the triangle. You had these 3 pieces given, you found the missing 3 pieces. But whether you fill that in here, that's fine. Well, if this was angle A over here, then side A, my 5.3 would go right here. Again, I didn't try and draw this to scale. These look like they're almost the same length, but they're getting very different side length values. It's just for reference, just so I could see this goes with this. If you want to label this as A and this is C, go ahead, but I could follow. As long as you have the angles labeled, then I could figure out which side is which. So I'm happy with that. So again, I did all of this at once, all this arithmetic, so I just rounded because I'm done here. That's my answer for side length A. And now let's do similar work for B. In this situation, technically now, you've got two side and angles that correspond to each other, so I could use either one, but the better habit, everybody, is to always use your original information. Technically, you rounded a little bit to get this answer. So by rounding to get this answer, if you use this answer to get another answer, now you're double rounding, and that's how little mistakes. Instead of getting a final answer of 6.2, you get 6.3, and why are you off a little bit? Because you double rounded. That can't happen. So the better habit, go back to the original pairing. And that's why I was saying, I started finding side A, but I could have just as easily found side B. I'd still have the sine of 84 over 8.7, but now for side B, I need sine of 59, sine of angle B, over little b. You do your cross multiplying, you'll see it works out very similarly. We'll get B is 8.7 sine of 59 divided by sine of 84. I mean, some people, you're using your calculator often enough here that it's not that bad to type this in, but some people, you notice it's so similar, you could do your second enter button and just change this angle. Now this has just become 59, but everything else is the same. 8.7 sine of 59, already have the parenthesis, divided by sine of 84, and rounding off, we would get 7.5 for B. So one more time, I'm perfectly fine with this setup, everybody. I could follow your work and see, okay, there are the three missing pieces, and to follow, that's angle C, that's side A, that's side B. That's perfectly fine with me. Other people going back to the original, well here, I mean, it's nice to put these things together. That's the side and angle that go together. So then little b would be 7.5. That side and angle go together. And little a is 5.3. I'm perfectly fine if you keep your answers there. Or, again, whether the picture was here or not, if you wanted to draw it. And just as I said before, it's perfectly fine if you want to keep all the sides and angles, but all I really need are your angles, your vertices labeled, and then I could follow to see you've got these in the right spot. Here's one little interesting aspect when it comes to checking your work. You are doing calculator work, so as we've seen, you start doing a lot of calculator work, you accidentally put a decimal in or miss a spot or put in an extra zero, how weird your answers can look. So just at the very end, do these answers make sense? All we have for that is just this little basic fact. The biggest angle we find should open up into the longest side, and the smallest angle that we have should open into the shortest side. And then if you want to throw in the middle angle goes with the middle side. And that's exactly what we see here. Biggest angle, biggest side. Second biggest angle, second biggest side. Smallest angle, smallest side. Now, again, if we got 7.5 and we should have got 6.9 because we made a calculator goof or something like that, we wouldn't catch that kind of mistake. But if we made something bigger and this came out to like 4.1, well, something's wrong here. But what went wrong? What did we find that was a mistake? That can keep varying. Okay, so again, a nicer problem, the way this worked out, that was just the perfect order. Getting angle C, but we got angle C by just looking at the sum of all angles adds up to 180, and then we used law of sines to get our missing two sides. Having this angle side relationship, using that, setting up our proportion to find the missing sides, one at a time. And by the way, everybody, any of the word problems follow this type of a setup. You know, something like, there's a fire in the woods. I have two fire stations keeping an eye out for forest fires that are 7.5 miles apart. This fire station sees the fire at an angle of 37. This fire station sees the fire with an angle of 84. Which fire station is closer and by how much closer? I mean, that situation is just getting us to draw this picture. And then realize, okay, well, this side is closer to the fire, and it's closer by 3.4 miles, something like that. And again, this really gets used. This idea of triangulation gets used for a lot of distance problems. And as long as you know the angles and a distance between 2 points, we could figure out so much other information. So I'm not trying to bust your chops with word problems here, just trying to point out that is how word problems would work here. But now let's get into our second situation. And the second situation is when we have one angle and two sides. But still, let me restate my directions. But now we're going to see something a little interesting happen. Complete the triangle with a possibility of triangles. And then there's an extra note, if any exist. So it feels like I've added more to my directions, and you'll see how and why that is in just one moment. But I'm still basically focused on complete the triangles, and we'll still round all angles to the nearest degree and all sides to the nearest tenth. And now, since we just slightly changed our directions, we'll call this problem number 1. Let's look at capital A is 43 degrees, little a is 81.1, and little b is 61.8. Okay, I did not draw a picture. You can if you want. But now, without even drawing that, just realize we're in a different situation than we were in the previous page. That now, only knowing one angle, there is no quick way to get a second, or certainly not the third angle either. And this is where a lot of common mistakes come up. Because now people are looking at A and B, and they go, hey, I can get C. A squared plus B squared equals C squared. That only works, that's Pythagorean Theorem, but that only works if you have a right triangle. And there is no good reason for us to assume this is a right triangle. It surely didn't tell us it's a right triangle. So again, that's not a good option. And the last bad option that people have, people just start doing Pythagorean Theorem with nonsense. People start doing 43 squared plus 81.1 squared. Where does the 43 fit in there? Pythagorean Theorem is all about side lengths, not angles. So, like I said, for multiple reasons, our only good option here is Law of Sines. But where do we start? The previous problem, again, we had two angles, so it made a lot of sense to jump right into the third angle, and that was especially necessary in the previous problem because the third angle, as soon as we found that, that corresponded to the only side. So we needed that side and angle that went together. But in this problem, we've already got an angle and side that go together. So I've got two pieces that go with one side of my proportion using Law of Sines. And by having side B, my first step has to be finding angle B. That's where we all have to go first here. Okay, you go back and look at that first one. If I gave you angle C and angle B and side C, there's a few little varieties. You could find angle A, or you could find side B. There's little variation, but here, this is what we have to do. So I'm setting up my Law of Sines, and as I said before, I always do what I know first. The angle and side that go together. So sine of angle A over side A equals, and now I know side B, and that has to go down here. My proportions have to be set up the same way, and sine of B will go up here. Now, solving this, it's still a proportion, so I'm still going to cross multiply, but solving for an angle here, because it has the sine function on it, is a little different than solving for the side length. I'll still cross multiply, so I'll get 61.8 sine of 43 equals 81.1 sine of B. And if I want to solve for B, well, I'll divide the 81.1 over. But now I need the angle. I have sine of B, I want B. How do I get rid of the sine? I take the inverse sine. And this is why this situation is going to be a little more difficult. So first thing, I hope so far it doesn't look that bad. We still use law of sines. We still had the angle and side that went together. And again, just different from the first problem. Before we knew the angle and wanted the side, well now vice versa, have the side and want the angle. But now solving, that's a little different. Even though this looks ugly, I could still do all this on my calculator at once. I'm already in degree mode. Inverse sine, 61.8 times sine of 43, close the parenthesis, divided by 81.1, and close the parenthesis for the inverse sine. Now, some people would rather do this in 2 steps. I did that all in one, and rounding to the nearest whole degree, remember this is an angle, so I'm not going to the 10th anymore, I'm going to the nearest whole degree. I would get B is 31 degrees. So, one quick thing, okay? First things first, just to point out back on the calculator, if you want to do this as a 2-step, that's fine. You can do the 61.8 sine of 43, close parentheses, that's still a must, divided by 81.1, and now do the inverse sine. But now, again, try not to round this off. Take advantage of your answer button. And we get the exact same thing we had a moment ago. But here's the pain in the butt, everybody. Now let's go back to the actual directions and notice why this felt a little different. Complete the triangle, possibility of 2, if any even exist. So now with these directions, we're really getting 3 possibilities, everybody. We might not get a triangle at all. The book does some nice little pictures. I'm not as good at drawing this, but you can be given information that it would just literally be impossible for the sides to connect. If you had this angle with this length and this length connects to it, there's just no way for a third side to connect. So that could happen. But here, that is not the case. How would we get a triangle doesn't exist? We'll see it. We'll do all this exact work, but we'll get an error message here. Remember, inverse sine only works on values between -1 and 1. We're never going to get any negatives here. We don't have any context where that would make any sense. But we can end up with something bigger than 1 inside here. So when you do inverse sine of that on your calculator, you get an error message. So if that happens, that means it's a bogus situation. There are no triangles. But as soon as we get this, now we definitely at least have 1 triangle, but we also have a possibility of 2. And this comes up because, again, the inverse sine function. When we made this function, we had to restrict the domain for the regular sine. So our calculator will never give us an angle bigger than 90 degrees. Remember, inverse sine will always get answers between -90 and +90. So with that, we would never understand an angle like this. That would never come out that we get an angle bigger than 90 degrees. But we know from triangle facts that can happen. So how do we make this work? This is it, everybody. I've said a lot, but this is really what it boils down to. If we need to find an angle first, the way we did it here, not an angle using the sum is 180, but the angle using law of sines, that's when the multiple possibilities present themselves. As soon as you get an answer, you definitely have 1. And if there's a second triangle, angle B, we have to think about the second quadrant angle. And the second quadrant angle with this as its reference angle, this second quadrant angle will always be 180 minus the reference angle. So if I do that here, I get 149 degrees. And now it feels like I have the 2 triangles. 1 triangle, here's the thing for everyone. All triangles, even if there are 2, Angle A, side A, and side B, those are set in stone. Those are not changing at all. But the other possibilities come up here. Once again, the book does some decent pictures to try and demonstrate this. I don't think they offer students a lot more full understanding, but to try and understand that these possibilities exist. They'll show you a picture where this works, and this is the angle for B, but how you could do this idea of a supplementary angle. Something like that if this is angle B over here is 31, then this could also be angle B over here, that's 149. And the situation over here with angle A and stuff could be reflected up here. So again, they draw some pictures to try and demonstrate that. But this again is just the simple short point. So B is 31 degrees, or is 149. Well, now I've got two angles. So now I'm using that these three have to add to 180. Well, these two add to 74, so that would leave 106 degrees for angle C. Just like we did on the previous, everybody. 43 plus 31 plus C equals 180. I just did a little bit of work to solve for C. But then I have to do that again. So angle A is 43. Angle B is 149. Does anybody see something majorly wrong here? If angle A is 43 and if angle B is 149, just adding those two together, I'm already getting 192 degrees. If we literally follow that formula, A plus B plus C equals 180, we would get C is negative 12 degrees. We're not looking at our standard unit circle, everybody. That negative 12 makes no sense. So that's the problem. If you end up, you got the first answer for angle B, so this is guaranteed. But now, here's the problem. We tried to think about a second possibility for angle B, and initially it looked like there was no problem, but then taking that second angle for angle B gave us a negative for angle C. This is all garbage. That means that angle, that second triangle, doesn't exist. And now we're back on track, and now we could realize that what I gave you in problem number 1 was a one solution triangle. Okay, we got one solution, and now let's finish it. We had angle A and side A. We found angle B to go with side B. And now finally we've got angle C. Let's find side C. And I'll still go back to my original, right? Now I've got angle B, so I could use angle B and side B as one side of my law of sines. But again, always better habit to go back to the original. So I'll still kind of use this setup. I'll have sine of 43 over 81.1. But now I do have angle C, sine of 106 over little c. And when I solve, do my arithmetic here, I got 114.3. And this is what I was saying. This is perfectly fine. I did my work on the sides. I could follow it. But ultimately, this is what I'm looking for. These three were given. These three were missing. And it all works. One more time. Just a quick check. Biggest angle goes with biggest side. Second biggest angle goes with second biggest side. Smallest angle, smallest side. That's as far as you can go, everybody. There are people who try and take this too far. They try and use these extra senses of proportion. They try and say things like, well, very roughly, 31 degrees is less than a third of this, so this side should be a third of this. That's garbage, everybody. Again, all it is biggest angle with biggest side and smallest angles with smallest side. That's as far as we can take it. Okay, let's continue. Number 2, let's look at angle A is 75 degrees. Little a is 50.8, and little b is 71.2. Almost the exact same startup as the previous. By having the angle inside given, and then one more side, just like the previous one, I have to use this along with this to get angle B. That's where I'm going to start. So sine of 75 over 50.8 equals sine of B over 71.2. Oh, I'm sorry, here we go. Sine of 75 over 50.8, sine of B over 71.2. I cross multiply, 71.2 sine of 75. The 50.8 would multiply to here and divide back over. I don't mind at all if you take the 2 steps, everybody. I did that on the first problem. I'm just going slightly faster, but again, no shame at all. Take the 2 steps to get this equals sine of B. And now I'll apply sine inverse to this. I received an error. It says error domain, quit, go to. It doesn't really matter. If you hit go to, it just goes back to your original work. So we have to have seen that to realize this answer doesn't exist. If I get rid of the sine inverse part, if I just do the 71.2 sine of 75, oops, sorry, let me start over. 71.2 sine 75 divided by 50.8. I do all that work, I get an answer bigger than 1. So yes, that's why when I do sine inverse of that, that's why I'm getting the error. So how do we finish this problem? We can refer that there is no angle B, but the best way is just now. Maybe you want to make that note again. Again, we're getting the error message, but that's not your final answer. You want to make some mention that there is no triangle. The triangle doesn't exist. There is no triangle. Something along those lines. And now let's just do one more, and I'll say a couple of quick things before we wrap this up. So problem number 3, still same setup, everybody. Now I've got A is 40 degrees, little a is 54.0, little b is 62.3. Same setup. This is the 3rd time now where I've been given one angle with 2 sides. I hope you realize, and I will point this out in just a moment, in this situation, I have to give you an angle inside that correspond to each other. But I'll come back to that in just a moment. So let's get right back into it. Just like here, sine of 40 over 54, 54.0, but that's the same as 54, over sine of b over 62.3. This one will work when I solve. I'll end up with the 62.3 sine 40 divided by 54. Sine inverse of that, that'll all give me angle B. This one will work. And again, everybody, that's why you just saw. Some people like to do the inner part first, so that way they already have a sense of whether it's going to work or not. Other people just do it all right off the bat, and they're just prepared. I would say if you get an error message, it's worth just taking a moment to go back and make sure you didn't goof with your arithmetic, accidentally plug something in incorrectly. But that's why, again, some people are comfortable doing this all at once and just knowing the results and how to move. Other people like a 1-2, doing this part, then coming and doing the inverse and already knowing, it's not going to work, it will work, okay? So that's your preference. So sine inverse 62.3, sine of 40 divided by 54, and I get 47.86, so I'll make that 47.9. I'm sorry, we said to the nearest whole degree, so that'll be 48 degrees. Now I know there's at least one solution. That's what we had here. Oops, I should have made that note on the side, the no triangle. So this one had no solution. But ultimately, these were the answers to number 1. This was the answer to number 2. But now, we definitely have at least one triangle, or I'll do the 180 minus 48 to get the second quadrant angle. That would be 132. And now I can move right into angle C. Well, if A is 40 and B is 48, that's a total of 88. That leaves 92 for C. Or if A is 40 and B is 132, those add to 172. There's not much left, but there is something left for C. C could be 8 degrees as well. That's the second triangle. We're getting, A is not changing. A is fixed, side A is fixed, side B is fixed, but angle B has 2 possibilities, and then correspondingly angle C has 2 possibilities, and now side C will finish with also 2 possibilities. Side C when this is angle C, and then side C when this is angle C. But we'll do both of those like we were right here. I'll go back to the original pairing. So I've got sine of 40 over 54, and I'll start with the 92, sine of 92 over C, and I'll get 54 sine 92 divided by sine 40. And this is the straightforward one, right? We've got the regular sine functions in here, no inverse sine. So 83.95, that would round up, that would become 84.0. Or just go up here. Instead of sine of 92, that will be sine of 8. Sine of 8. It's certainly fine to set it up all over again. I'm just trying to squeeze this in here. So I'm just finishing up right here. Same exact work, just again, just changing that to sine of 8. I get 11.69, so that'll be 11.7. And even in the 2 triangle situation, in my first triangle, A, B, and C, biggest angle, biggest side, second biggest angle, second biggest side. And then in my second setup, this is the biggest angle, and when this is the biggest angle, this is the biggest side. This is the smallest angle, that is the smallest side. So we can still use that little relationship. Okay, everybody, so I want to finish on this note. The second bunch of situations, it's definitely a little bit more of a pain. Knowing the 2 angles is certainly the more ideal. And like I said, any word problems, that would certainly be the case. But I just want to finish this video with one quick note. I just want to point out, what happens if you knew something like this? What if I knew angle A, and I knew side B and side C? Where do I go from here? How do I even start? Law of sines, unfortunately, doesn't work here. So we're not going to do any problems with this. I just want to point this out. This is where we would need the law of cosines. The law of cosines almost looks like Pythagorean theorem, but it applies to any triangle. It starts with this generic c squared equals a squared plus b squared. That looks like our perfect Pythagorean theorem. But then you get this minus 2ab cosine of angle C. And this is where I can play more games here. And now, if I know, I mean, this goes in all different situations. If I knew all 3 side lengths, if I knew lengths of A, B, and C, I could use this to solve for cosine of angle C. And then I could use law of sines to get angle B, and then just use my sum of the triangle angles to get angle A. That's one way that this can go. Or in something like this, well, I could rearrange this a little bit. Instead of using the c squared equals a squared plus b squared, I could rearrange this as a squared equals b squared plus c squared minus 2bc, cosine of angle A, and I could use that to find side A. So again, a very useful section, but for our purposes, stick with the just basic idea of completing the triangle. The multiple triangle questions are a little weird, but get a little practice and you'll be very well off for this section.